we continue to talk about the MRI. We already talked about the protons have charge and is spinning. Then it can be treated as spinning magnet bar. So if there is external magnetic field, they will line up with the magnetic field. However, only have external magnetic fields, it still cannot get the MRI image. So how to create MRI imaging? That we need electromagnetic fields. Okay, that's important. So what these electromagnetic fields do? In fact, we need these electromagnetic fields to perturb the nuclear, okay, to manage the magnetization. This kind of electromagnetic fields from outside, they oscillated at frequency generally is tens of millions of times per second. So these RF fields will put there, then can perturb the proton. Okay, then based on that, we can merge the net magnetization of atomic nuclei in the presence of magnetic fields. Let's see how it is done. Let's first explain the radio frequency fields. Just now we say we need the electromagnetic fields from outside to manipulate the magnetization of specific type of atoms. Not all of the atoms. Oh, because some atomic nuclei are sensitive to magnetic fields. Okay, and their magnetic properties are turned to particular I frequency. So if there is external RF waves transmit to the subject to perturb this nucleus, this perturbed nucleus will generate RF signals at the same frequency. So this frequency can be detected come out of the subject. Then we can use them to construct image. Okay, let's see how the external radio frequency perturb the nucleus. We know some protons, if there is no external RF wave, they are in no energy status. If there is external radio frequency to put here, they will jump to high energy status. Okay, that means they just get some energy different from the lower energy status, jump up to high energy status. That's basically physics. When you receive the external radio frequency. However, when some proton is jump from the high energy status to low energy status, definitely there is some energy exit. This energy exit, they will generate RF radio frequency to outside. Then we can use some machine to merge this radio frequency. Then we get the MR signal. This MR signal can be used to construct the MR image. Okay. Let's show the basic idea. First, let's see about there is no radio frequency from outside. We just have a external magnetic field B0 here. Okay, this is a proton. Some proton is go up, some proton is go down. Okay, the direction. I means the magnetic fields of the proton. But there is a net magnetization. Okay, net magnetization, because some field go this direction, some go the other direction, but the net magnetization M, okay, is depend on 0, B0. This is the mass to compute M. So from here we found that M depend on B0. So generally, if generally small B0 produce small net magnetization M based on the formula just now, larger one produce larger net magnetization. Okay. So however, that is the external B0 make this proton line up with the what? With the external magnetic field B0. However, also the proton is spinning, it's moving, because depend on the temperature. If temperature is low, they are moving slowly. If the temperature is high, they're moving fast. So generally the thermal motion try to randomize alignment of the proton magnets, but the B0 is making line up, but the thermal motion renders the alignment. They are against each other. Okay. So some is go up, go the direction with B0. Some go north the direction 0. So there is, that means some is antiparallel, some is parallel. The two type protons. Some is antiparallel with the B0. Some is parallel to B0. So what's the ratio? The ratio at room temperature generally is 10,000 to 10,006 per Tesla of B0. That means we have the net magnetization will create by the 6 protons. Okay, 6 other 10,000, because the parallel and the antiparallel, they are the same. Okay, we just have 6 more. So this 6 more is will create the pure the net magnetization. Okay, so that's always talk about we have net magnetization. So how to measure the magnetization? Generally, we cannot measure the magnetization. We can only measure the magnetization perpendicular to the B0 field. So that's the issue. Currently, net magnetization is parallel to B0. So we need to do something to apply the energy to keep the protons out of the alignment. Okay, that's what we need, the radio frequency. okay, from outside to tip the protons, the net magnetization away from the B0. So how much the energy we needed to make it tip away from the alignment? That depends on nucleus and applied field streams. Generally we call it gamma frequency. Also, the amount of energy added, okay, determines how far the net magnetization will be tipped away from the B0 axis. If the amount of energy is big, then they can tip away from the B0 axis a lot. But a small amount of energy, they will not. Okay? The amount of energy is measured by the duration of the RF pulse at the resonant frequency. So that is how we can merge the magnetization. That's first we need to perturb it. In fact, just now the M is parallel to B. Okay? If it's M is the net magnetization. If M is not parallel to B, what does M moving? This net magnetization, if it is not parallel to B, they will process clockwise around the B direction. Okay? Just from here, then go here. Okay? So if the M, that means here M0 and MX is not 0. If M is parallel to B, that means MXY will be 0. Okay? For MI image, you guys will know we need to tip the M from the direction of B to Y direction. That we will see in next several slides. So let's see the basic idea. So currently the net magnetization M is parallel with B0. Okay? B0. So think about this one. If we add radio frequency from outside, this energy will be added here. Then this radio frequency will be perturb this proton and make the MR process to tip away from the B0 direction, currently the Z direction, to go to the Y direction. Okay? First they will go here, and then will come to here, then will come to here. Okay? So the issue is when you every tip away to something, that magnetization still also process around the Z direction. Okay? So this will be the whole process like this. First you tip a little, then also a spin, not spin, is a rotation. Then tip more, then this will be also will process. Tip here also will process. Tip here process. Also the same, tip here process. Okay? So that's if we put the rhythm frequency, the energy is big, they will tip a lot. Okay? So that's the basic idea when apply an RF pulse. The question is when this RF pulse can be effective. Only the frequency is the same as the frequency inside the atom to the atom inside the human body. Okay? So this is turn off the RF frequency. If we turn off, for example, this RF turn off, what happen? If we turn off this the RF from outside, then the RM, okay, the still will be rotate around the z direction, but it still go from the y direction go to the z direction. They try to go back in this way, because in this way they will be jump from the high energy stages to the lower energy stages. Then they will transmit RF energy out. Okay, but this time at the resonance frequency. Okay, resonance frequency, the same frequency as the radio frequency just now. You come to the human body. Now the human body exceeds that frequency. So this RF frequency is really the MR signal. Okay, you can merge the RF signal, then use them to reconstruct the MR image. So just now we talk about the basic idea. So how to create the MR image? There are very complex mathematics there. Okay, what I talked just now, we need several things for the MR image. The first one, we have some spinning proton with charge, and the number of all proton should be ordered. So hydrogen is the best atoms, okay, for MR image. The second one, we need the external fields. Okay, external fields make because the proton can be treated as spinning magnet bar. Okay, if there is external magnetic field, they will line up with the external magnetic field. Okay, so even you have external magnetic field is not enough, because what we really measured is not the net magnetization. We will know what we really measured. There are several ways we want to measure it. Okay, we will measure the relaxed time of the net magnetization. What's the relaxed time? We know after we put the radio frequency on the side to excite the spinning protons. Okay, first the spin, let's explain like this one. First, the spinning protons with charge, they create a little magnetic field every protons. Okay, these protons then line up with the external B0, external magnetic field B0. Then we put the RF excitation there. Okay, after this excitation, okay, then the net magnetization will keep away from the B0 direction. Okay, so the relaxed time is like this one. Okay, when the two relaxed time, one relaxed time is like this one. When they if we let's express let's explain let's do this way. Let's first explain the T1 relaxation. Okay, after that we can know what's relaxed time. So first, like this one, there is the protons create net magnetization. Okay, it's here, the yellow line here. So that means the protons with spinning protons with charge. Okay, when there is external magnetic field, then they will create a net magnetization. Okay, that's the yellow bar. So if there is a thermal RF wave, okay, this RF pulse will act to the human body. Then first they will tip away, okay, this net magnetization tip away from the D direction. Okay, if we put the energy is enough, then this yellow line will go a line with the y direction. Okay, the degree from the yellow and z will be 0. The red line here, you guys see here, just show here. That means show the net magnetization. That means the absolute number of the protons which has the direction with z direction are more than the number of the with the anti z direction. Okay, but if we come to the if we tip the net magnetization to the y direction, that means the direction, the protons numbers which has the direction with the z and in the anti-z direction would have the same number, so they will go to with the y. So when you do stop the radio frequency, okay, then this yellow line will go back to the z direction. Okay, go back to the z direction, because just how B0 exists, the RF pulse is not there. Okay, so B0. So this net magnetization will become bigger and bigger, then become. Okay, so we called the time generally they recovered. So it recovered the net reaction in z direction recovered from the direction y. Okay, this time we called T1 relax. Okay, recovered, that means this signal recovered, that's called T1 relaxing. Okay, the time they used to, in fact the time relate to the whole time, relaxed time. Okay, we can say the T1 relaxed time. Okay, from here to relaxed, that's recovered to his one. Okay, take some time from here, then to here, take some. This time we talk T1 relaxed time. But the real time we want to in MR image to merge this the MR signal, they use the 67% of the whole time. We call it T1 time. Okay, T1 time. T1 time, not the whole time from here to here. Okay, not the full recovery. They just say it's 67% the time. We call the T1 time. If you guys go deeper, you will know the exact T1 time. Okay, so this is the recover, the net magnetization, the recover from this to here. That's called the T1 relaxing. Also, we have a T2 relaxation. T2 relaxing is totally different. Okay, that means this signal. Okay, first they will recover this one, then this direction there, net magnetization will become smaller. See here, smaller, then become 0. Okay, so this net magnetization from this direction to become 0, this whole process is called T2 relaxation. Okay, what's the T2 relaxation? What's the T2 time? We called 34% of the T2 relaxed. We call it T2 time. That means if this is the whole time for this net magnetization disappeared to 0 with some time. So the 34% of it we call the T2 time. Okay, so we can merge the T2 time, T1 time, and T2 time. Different tissues have different T2 time and also T1 time. So based on these properties, okay, then we can create different MR gray value. Okay, for example, some tissue is cancer, some tissue is not cancer. The tissue cancer has some T2 time. It's different from the normal tissue's T2 time. So we can match these 2 times, then create different image intensity. The same, different tissues all have different T2 time. So cancer has cancer's T1 time. Normal tissue has normal tissue T1 time. So we also invert the T1 time to create a different image intensity for cancer and non-cancer. Then when you see the image, you can find where it's cancer, where it's not cancer. Okay, so there are several types of images. Sometimes we call the T1 weighted image, MR image. Sometimes it's called T2 weight MR image. For this one, it's a little difficult for you guys to understand. Okay, but what I want you guys to know is just basic idea for the MR image. I will put some material for you guys to read to more understand. If you have a question, can tell me. Okay, so this is just show some MR image created by I got from some place. Okay, so that's for today. Okay.